Hello everyone. I'm participating from Turkey, where I'm lecturing at Yozgat Bozok University. Today, I would like to talk to you about model predictive control implementation for the permanent magnetic synchronous motors, where it is used for light railway applications. Uh, Why is not here? First thing first. I would like to summarize the scope of this study, where I am going to speak a little bit about motivation of the research. Following that, I will mention PMSM round motors and some challenges about these motors and implementation of model predictive control. Then finally, I will illustrate some figures from my simulation. I'd like to start with a brief introduction. This research study is proposed permanent magnet synchronous machines, and in this investigated the requirements of railway traction system. The railway traction motors have the same operating principle with the stationary application motors, but the volume of the proposed motor is quite important because for the transportation application, uh, because of the its mobile application. Therefore, the power density and efficiency of the machine are the key properties for vehicular applications. In the light of these requirements, we concluded that use of PMSM machine is proposed for railway applications, and the focal point of the study is implementation of model predictive control methods for PMSM machines. So let's move on to the reason of using PMSM. Because those are getting popular amongst the other motors for transport applications and gaining some attention for railway traction because railway traction motors have typically a requirement of high power density, as we said, uh, and also efficiency is important. Therefore, the highest power density of PMSM motors compared to motors is seen as a clear advantage for traction application. It also has only stator windings and there's no windings on the rotor. It also doesn't include any brushes. Therefore, heat generation is low compared to with brushed motors. It may also offer a smaller size for more compact mechanical packages. So PMSM highly useful for industrial and vehicular tasks. Now we come to the challenges that we are facing by using PMSM and possible methods to overcome these issues. Firstly, reliability and robustness aspects of the power conditioning unit, uh, where we can think about the field-oriented control, the maturity and the performance of this controller for motor drive applications are, undeniable facts. However, there are some sophisticated and potent options to deal with multivariable parameter monitoring, which can be managed by model predictive control, which is discussed in this study. Uh, Also, whenever we think about the faulty operating condition for the motor, where the motor keeps spinning because the rotor is still connected onto the shaft in a vehicular application, then problem arises because of the magnetic materials have still induced some voltage over the faulted windings. And using a mechanical clutch for disconnecting the motor from shaft or applying recommended field weakening method, which is recommended for the whole speed range rather than the after the base speed, can mitigate these issues. Then I'm going to move on to the difference between the surface and interior PMSM machines. In terms of the demagnetization of magnet, same amount of torque with less current is desired to protect magnetic feature of the magnets. Therefore, almost the same torque with less current must be, the the trade-off against the additional complexity in the design of interior magnet machines. It also, these machines, interior magnet machines, can operate with smaller current and which has then have higher efficiency or can be designed with smaller coils, which reducing the volume and the cost of the design of the machine. So let's turn to the field-oriented control. In order to achieve the better dynamic performance, a more complex control scheme needs to be applied to the control to control the PM permanent magnet machines. The use of mathematical transformation to control the AC machines is like DC machines, which providing independent control of the flux and torque producing currents. Such decoupled torque and magnetization control is commonly called field-oriented control, where the system inputs like IQ dash, ID dash are compared with the feedback currents, which is IQ and ID, to determine the current errors. The errors are applied to the two controllers to provide the Q and D axis voltages, which result in VQ dash and VD dash commands. How about the MPC model predictive control? Here in the system is controlled with a prediction model and a reference state at every single sampling time, where there exists an optimal solution for the control horizon with a certain time frame. Here, a cost function, a converter predictive model, and a load model are the three primary components of an MPC. The motor itself serves as the load for the PMSM control. Here in this figure displays the block diagram of the whole control arrangement. I'm gonna move on to the some results from the simulation. From this chart, we can understand the PMSM has quite similar acceleration rate while controlled by both MPC and field-oriented control. These figures illustrate the acceleration rate of the PMSM. There exists a smooth transition from transient response to steady state condition, and the error is pretty small for both techniques. Let's have a look at the ID and IQ currents. Here in these slides, ID currents are also set to 0 because the type of the motor is round rotor, which is used in this research. Then implementation of the ID is equal to 0 current control. There the current follows the reference as given in the figures, figure A and B. The current waveform has lots of oscillation at figure A, which is between plus and minus 10 amps for the field-oriented control, while these fluctuations are reduced between plus and minus 2 amps with the MPC controller. Here in this part, it's important to note that there exists a quite big spike at figure B at the initial operation of the MPC controlled machine, but this wouldn't last a long period and is compensated at the beginning of operation. Additionally, whenever speed reaches to the rated value, the measured ID current doesn't fluctuate during the steady state condition, and there exists nearly 0.5 amps error as given in the figure B. For the IQ currents, graphs are given in these figures, where current oscillations around 260 to 280 amps can be observed during the acceleration period from 0 to 15 seconds for figure A, while these fluctuations are decreased massively by using MPC, which is given in the figure B. On the other hand, there exist oscillations both in MPC and field-oriented control during the transition period, which is between 15 to 25 seconds, because of the transient response of controller. However, these oscillations are also relatively less for the MPC, since it starts between 80 to 240 amps, whereas this range is 50 to 260 amps for the field-oriented control. After the given fluctuation period, the MPC shows better performance compared to field-oriented control during the steady state condition, which is from 30 to 40 seconds. The current IQ varies between 150 and 170 amps in figure A, while this value is around 162.5 roughly amps for the MPC, which is given figure B, even though the existence of the steady state error for the MPC. I would like to conclude some points. We could clearly see from the simulation results that the control architecture has an important effect on the current ripple and the ripple relevant to the current, such as power and torque. Those fluctuations are linked with power losses and have, crucial importance for the traction system efficiency. And the system is more effective for the traction situation in the real world because of the enhanced current tracking and less ripple, which immediately result in fewer energy losses for the MPC. According to these findings, MPC can greatly improve the robustness and the performance of the electrified railway systems, especially those that use fuel cells or batteries as catenary free energy sources. For the next step, this study is going to carry on with MPC for double three-phase PMSM, which will be simulated in a real-time simulation as a next step. This is going to be test on a hardware in the loop system to design the programmer controller board to have a more realistic and more reliable system. So that's all from my side. Thank you for your listening. If you have any question, please raise your hand, or you can catch me in a breakout room or email me. Thanks. That's all from my side.